All right, let's dive in. Today, we're going to explore the amazing world of spectroscopy. We're going to figure out how scientists can identify pretty much any substance just by reading what you can think of as its unique molecular fingerprint.
I mean, think about it for a second. Our world is literally built from countless molecules, and almost all of them are completely invisible to us. So how do we know what's really in our water, or in the air we breathe, or what's happening inside a chemical reaction? How do we possibly identify something we can't even see?
Well, the answer is actually pretty cool. We do it by reading their unique molecular fingerprint. You see, just like no two people have the same fingerprint, no two types of molecules interact with light in the exact same way. And that special interaction, that's what we're going to decode today. So, we've got this idea of a molecular fingerprint. But what is it really? And how do you even begin to read it? Well, the science that lets us do all of this is called spectroscopy.
At its very core, spectroscopy is just the study of how light and matter interact. That's it. When a beam of light passes through a substance, that substance will absorb some of that light and just let the rest pass right on through. By analyzing exactly which bits of light get absorbed, we can figure out precisely what that substance is.
So why is this method so incredibly useful? Well, for starters, it's super fast and unbelievably sensitive. Plus, the results are reliable, creating a permanent record, kind of like a snapshot of that molecule. And maybe the best part? You only need a teeny tiny amount of a substance to get a reading, and a lot of the time, you can even get that sample back when you're done.
You know, to read these fingerprints, scientists needed a language that molecules could speak. And it turns out that language was light itself.
Okay, so here's the fundamental principle. Imagine you're shining a beam of pure white light, which has all the colors of the rainbow packed inside, through a glass of, say, a colored solution. The molecules in that solution are picky. They will grab or absorb very specific colors, very specific wavelengths of light, and let all the other colors pass right through. What we're measuring is the light that doesn't make it to the other side.
Now, there are really two main ways to look at this whole thing. You can look at the light a substance gives off when you energize it. That's called an emission spectrum. The perfect example is a neon sign glowing. Or you can look at the light a substance soaks up from a source. That's an absorption spectrum. And for the rest of this explainer, that's what we're going to be zeroing in on.
So what's actually happening on a molecular level when it absorbs light? I mean, why is it so picky? Why does it only absorb very specific amounts of energy?
It turns out a molecule can use the energy it gets from light in three main ways. If you hit it with high-energy light, like UV light, it can cause an electron to literally jump up to a higher energy level. That's an electronic transition. If you use less energetic infrared light, you might just cause the chemical bonds to stretch and bend, like tiny little springs vibrating. And with even lower energy light, you can simply make the whole molecule spin faster.
Let's focus on that first one, the electronic transition. As you see here, an electron is just chilling in its home energy level. When a photon of light comes along with the exact right amount of energy, the electron absorbs it and uses that energy to leap up to a higher, excited state. It's kind of like needing the exact change to get on a bus. A penny more or a penny less, and you're not getting on. And since every single molecule has its own unique set of energy gaps, each one needs a different bus fare, and that's a huge part of its fingerprint.
Okay, so this is all great for figuring out what a substance is. But spectroscopy can do more. It can tell us how much of something there is. And to do that, we need to get into the laws that govern how much light gets absorbed in the first place.
It really just comes down to two simple, super intuitive ideas. First, Lambert's law says that the thicker the sample is, the more light it's going to absorb. That makes total sense, right? The light has to fight its way through more molecules. Then there's Beer's law, which says the more concentrated the solution is, the more light it'll absorb. Again, that's exactly what you'd expect. More molecules packed into the same space means more light is going to get blocked.
And when we combine these two common sense ideas, we get the incredibly powerful Beer-Lambert law. This simple-looking equation is really the engine that makes quantitative spectroscopy work. It directly connects the absorbance, the thing we measure, to the concentration. The real key here is that constant epsilon, also called molar absorptivity. You can think of it as a special number that represents how strongly a specific molecule absorbs a specific wavelength of light. It's another core part of its fingerprint. And because it's a known value for millions of compounds, we can use this equation to figure out a substance's concentration with amazing precision.
All right, enough theory. Let's see how this amazing tool is actually put to work out in the real world. How do scientists take these principles and turn them into actual, useful results?
So the workhorse here is an instrument called a spectrophotometer, and it's a really clever setup. Light from a source passes through a device that picks out just one specific wavelength, one color. That single color light then gets split. One beam goes through a reference, which is usually just the pure solvent. The other beam goes through our sample, and a detector at the end measures how much dimmer the sample beam is compared to the reference. That difference, that gives us our precise absorbance value.
And just in case you're wondering how fundamental this stuff is, take a look at this. This is a question from a real engineering exam asking students to discuss the whole shebang, the principle, the instruments, and the applications of UV spectroscopy. So yeah, this isn't some obscure technique, it is absolute core knowledge for scientists and engineers everywhere.
So where do we see this in action? Oh, just about everywhere. It's used to make sure life-saving drugs are pure by detecting the tiniest trace of an impurity. Environmental scientists use it to monitor the health of our planet's ozone layer. It's a critical tool in forensics for identifying unknown substances at a crime scene. In labs, it lets chemists literally watch chemical reactions happen in real time. The versatility is just mind-blowing. So, let's just end with this thought. By learning to read the language of light, we've basically gained the ability to see the invisible. If every single molecule out there has its own unique fingerprint, its own story that it tells through the light it absorbs, what other invisible stories are just waiting right now to be read all around us? Thanks for tuning in.